Welcome to all of you in this lecture. In this lecture we will define conjugacy class of an element. We will see its relation with normal subgroup. We will also define conjugate of a subset, conjugate of a subgroup and conjugacy class of a subgroup. So let us start now. So suppose G is a group and XY are two elements of the group G. We say that Y is conjugate of X if there exists a G in G such that Y can be written as GXG inverse. So Y is equal to GXG inverse. So it means if Y is conjugate of X, then Y is equal to GXG inverse. So any conjugate of X is of the form GXG inverse. So let us collect all the conjugates and make a set, and that set is called conjugacy class of X in G. We will denote that set by CLGX. This notation may vary from book to book, but we will use this notation for our lecture. So CLGX is the conjugacy class of X in G. This is also called conjugate class of X in G. It is the collection of the elements of the form GXG inverse such that G belongs to G. Now let us define a relation on G as two elements X and Y of G are said to be related. So X is related to Y if Y is conjugate of X. We will see that this relation is an equivalence relation. So let us first see that this relation is reflexive. So because X can be written as EX E inverse, where E is the identity element of the G, so this relation is reflexive. Suppose XY are two elements of the group G and X is related to Y. It means that Y is conjugate of X, so Y can be written as GXG inverse for some G in G. So we can take this G this side and this G this side. So X can be written as G inverse Y G. So X can be written as G inverse Y G inverse inverse, where G inverse is an element of G. So it simply means that X is a conjugate of Y, so Y is related to X. So this relation is symmetric. So whenever X is related to Y, Y is also related to X. Now take three elements X, Y, Z in G. Suppose X is related to Y and Y is related to Z. Then Y is conjugate of X and Z is conjugate of Y. So we can write Y as G1X G1 inverse and Z as G2Y G2 inverse for some G2, G1 and G2 belongs to G. So Z can be written as G2Y G2 inverse, and in place of Y we can write G1X G1 inverse. So it means Z can be written as G2 G1X G2 G1 whole inverse. So it means Z is related to X, but relation is symmetric, so X is related to Z. So what we have shown is that X is related to Y and Y is related to Z, means X is related to Z, so this relation is transitive. So this relation is an equivalence relation because it is reflexive, symmetric and transitive. For each equivalence relation we can define an equivalence class. So the equivalence, suppose X is an element of G, then the equivalence class of X is denoted as the bracket X. Then this bracket X is nothing but those Y in G such that X is related to Y. So this is those Y in G such that Y can be written as GXG inverse, where G belongs to G. So in place of Y we can write GXG inverse. So this bracket X is equal to GXG inverse such that G belongs to G. But it is the same thing as the equivalence class of X in G. So the equivalence, this is the same as the conjugacy class of X in G. So it means the equivalence class of X in G is the same as the conjugacy class of X in G with respect to this relation. So but one thing we know that equivalence relation partition the set, and because this is the equivalence relation, so it will also partition the set. Now let us understand this thing by example. So suppose I take a group G to be V4, that is Klein's 4 group. Its elements are E, A, B, C. So let us determine the conjugacy class of each of its elements. Note one thing, that this group is an abelian group. So whenever we take one element, suppose I take one element A in this group and I calculate G inverse, then because it is an abelian group, so we can shift this element here and this element here. So we can write it as G inverse A, but then G inverse will cancel out and we will get A. So it means whenever we will take any element and determine its conjugacy class, it will remain the element, it will give you the same element. So it means for each element in V4, if you will determine the conjugacy class, because it is abelian, so we will get the same element in that class. So the conjugacy class of A will be A, conjugacy class of B will be B, conjugacy class of C will be C, and similarly conjugacy class of identity will be identity. And as you know, identity is always commuting with every element. So for any group, if you will calculate the equivalence class of identity, then it will remain as identity. So this V4 is partitioned into 4 equivalence classes, that is equivalence class of A, equivalence class of B, equivalence class of C, and equivalence class of E, and this will happen for every abelian group. The number of equivalence classes will be same as the number of elements in that group. So now come to an example of non-Epilen group. Suppose I take S3. So S3 has 6 elements. So equivalence class of identity, as we have seen, will comes to be the identity itself. Now come to the equivalence class of 1, 2, that is the same as the conjugacy class of 1, 2, and it is the collection of elements of the form G, 1, 2, G inverse, where G belongs to S3. So I am leaving it as exercise to verify that it turns out to be 1, 2, 1, 3 and 2, 3, and which is same as the equivalence class or conjugacy class of 1, 3 or the equivalence class or conjugacy class of 2, 3. Similarly, take another element 1, 2, 3 and determine its equivalence class, that is same as the conjugacy class of 1, 2, 3. So it is the collection of the elements of the form G, 1, 2, 3, G inverse, G belongs to S3. So now it is exercise for you to calculate it. It turns out to be 1, 2, 3 and 1, 3, 2, and which is the same as the equivalence class of 1, 3, 2. Now the whole group S3 is partitioned into 3 parts. One is equivalence class of identity, another is equivalence class of 1, 2, and another is equivalence class of 1, 2, 3. Or you may say it, one is the conjugacy class of 1, another is conjugacy class of 1, 2, or conjugacy class of 1, 3, or conjugacy class of 2, 3. Similarly, the last one is the conjugacy class of 1, 2, 3 or the conjugacy class of 1, 3, 2. So the whole set get partitioned into 3 parts. Now let us take one more example. Take G to be Q8. It has 8 elements. So 1 and minus 1 are in the center, so they will commute with all the elements. So they, in their conjugacy class there will be a same element. So conjugacy class of identity is 1. Conjugacy class of minus 1 is minus 1. Now conjugacy class of I is Gx, G inverse type of elements, where G belongs to Q8. One thing you can notice that the inverse of I is minus I, inverse of J is minus J, and inverse of K is minus K, inverse of minus 1 is minus 1, and inverse of 1 is 1. So you can put G inverse accordingly and calculate it. So we will get 2 elements I and minus I in the conjugacy class of I or equivalence class of I, and which is the same as the equivalence class of minus I. Similarly, equivalence class of J and minus J are same, and this is equal to J minus J, and equivalence class of K and minus K is same, and it is equal to K minus K. So when you will write it, then you will get that there are 5 equivalence classes of Q8. One is the equivalence class of 1, another is equivalence class of minus 1, and then equivalence class of I, equivalence class of J, and equivalence class of K. So this whole Q8 get partitioned into 5 equivalence classes or 5 conjugacy classes. Now let us see the relation of it with normal subgroup. So suppose G is a group and N is a normal subgroup of G, and take one element n in n and g in g. Then what will happen, because n is a normal subgroup, so g and g inverse will belongs to n. And this is true for all g in g. So it means if we collect all these elements, g and g inverse such that g belongs to g, it will be contained in n. So it means the whole conjugacy class of n will be inside capital N. And this is true for all small n in capital N. So take any element small n in n and take its conjugacy class, it will be contained inside n. So if n is a normal subgroup, then n contains conjugacy class of each of its element, and its converse is also true, because if n contains conjugacy class of each of its elements, then the reverse implication, by the reverse implication, g and g inverse belongs to n for all g in g and for all n in n. So it means this n is normal subgroup. So this is if and only if condition. If n is a normal subgroup, n is a normal subgroup if and only if n contains the conjugacy class of each of its element. Symbolically, it can be written as n is normal subgroup of g if and only if conjugacy class of x in g is contained in n for all x in n. Let us understand it by example. Suppose I take the group S3 and take a subgroup H to be identity 1, 2. Now I take one element identity and its conjugacy class is identity itself, it is contained in H, no problem. Take another element 1, 2 and the conjugacy class of 1, 2 has three elements 1, 2, 1, 3, 2, 3 which are not contained in H. So it means H is not a normal subgroup. Now let us see the relation between conjugacy class and centralizer. So recall that centralizer of an element x is defined as g in g such that gx is equal to xg. It means the collection of all those elements which commute with x. So if you recall the lecture group action 4, and after 12 minutes it has been shown that if G is a finite group, then the order of conjugacy class of an element x in G is equal to the order of G upon order of centralizer of x in G. Order of G upon order of centralizer of x in G is also called the index of the centralizer of x in G. So it means the order of the conjugacy class of x in G is equal to the index of the centralizer of x in G. One more thing has been proved in this lecture group action 4, and that thing is if G is infinite group, even then there is a one-to-one correspondence between the conjugacy class of x in G and the number of left cosets of centralizer of x in G. Now let us see it by an example. Suppose we have a group S3 and I take one element 1, 2. Then the centralizer of 1, 2 is identity 1, 2 and the conjugacy class of 1, 2 has 3 elements. So you can see from here that 6 by 2 is equal to 3. So the formula is verified. And of course index of centralizer of x in G is equal to the number of conjugates of x in G. So now let us define the conjugate subset. So suppose I have two subsets H and K in G. K is conjugate to H in G if there exists a G in G such that K can be written as GH G inverse. Similarly, we can define the conjugate subgroup. So we say that K is conjugate of H in G if K can be written as GH G inverse, where H and K are the subgroups of the group G. Now similarly we can define the conjugacy class of a subgroup. So suppose H is a subgroup of the group G, then the conjugate class or conjugacy class of H in G is denoted as CLHG, and it is defined as the set of subgroups of the form GHG inverse such that G belongs to G. So now we will see the relation between the conjugacy class of a subgroup and the normalizer of a subgroup in the next lecture. Thank you. Till then,